In this video, we are actually going to talk about sequences. We'll talk about what they are and how to work with them. We'll look at their definition, and we'll look at a few examples. So first of all, let's start with a definition. And it may not come as a surprise that a sequence is just another kind of function. So it's a function, but unlike most of the functions that we look at where the domain is either all real numbers or most real numbers, in this case, a sequence is a function whose domain is the set of natural numbers. So natural numbers are the numbers 1, 2, 3, and so on. In other words, positive whole numbers. So the values of this function, or the outputs, I guess we could say. So we have f of 1, f of 2, f of 3, and so on, are the terms of the sequence. And rather than being written f of 1, f of 2, f of 3, they're usually written as a sub 1, a sub 2, a sub 3, and so on. So a couple quick things. So a sub 1 is called the first term of the sequence, and then a sub n, which a sequence can have infinitely many terms. It doesn't have to, but it can have infinitely many terms, and this is called the nth term. So you'll notice that a lot of the problems that we encounter do one of two things. They either give us the nth term and then ask us to either find a few terms or something like this, or they give us the first few terms and they ask us to find the nth term. So let's look at a couple examples and talk about some basics along the way. So example 1. Let's say that we have a sequence where the nth term is simply defined as n plus 2. Okay? So the nth term is just the number n plus 2. So, for example, a sub 1 would be 1 plus 2, which is 3. A sub 2 would be 2 plus 2, which is 4. A sub 3 would be 3 plus 2, so that's 5, and so on. Okay? Here's another example. So you could have a sequence that's defined in a slightly more complex way. So we could have something like this. Negative 1 to the nth power divided by n minus 1. And let's actually say n minus n plus 1. And the reason I don't want to do n minus 1 is that then we have an issue with the very first term, and I kind of want to avoid that. So we have negative 1 over n, negative 1 to the power n divided by n plus 1. So what's important here is that when you raise negative 1 to a power, and the power is a natural number, you are always going to get either negative 1 or 1, depending on whether the power is even or odd. So what you are going to see here is, since natural numbers alternate between even and odd, even and odd, even and odd, you are going to see what's called an alternating sequence. So, for example, a sub 1 Well, negative 1 to the first power is just negative 1. And then 1 plus 1 is 2. So the first term of the sequence is negative 1/2. A sub 2, so now you're squaring negative 1. Okay, and when you square negative 1, you get positive 1, and then divided by 2 plus 1, which is 3. So the second term of this sequence is positive 1/3. Let's just do one more to make sure that we get the gist. So now we're cubing negative 1. We're back to negative 1 again, and then we're dividing by 4. So we can see here that for even values of n, or I guess I should say even values of n like 2, the term of the sequence is positive. And for odd values of n, like for example 1 and 3, the term of the sequence is negative. So that's called an alternating sequence. Another kind of way to define a sequence, and we'll look at two different examples of this, is something that's called recursively defined. Okay, so recursively defined sequence. So you might have something like this, like a sub n is equal to a sub n minus 1 divided by 3. And the first term is negative 10. Okay? So in recursively defined sequences, you are going to be given some way to define the nth term based on terms that came before it. It could just be 1, it could be more than 1, so we'll look at an example in a minute of a pretty famous sequence where the recursive definition involves 2 terms. And so let's try this. We are given the first term, so a sub 1 we know to be negative 10. So let's look at what a sub 2 is. Well, a sub 2 is a sub n minus 1 over 3. Well, a sub n minus 1 here is a sub 1. So that's negative 10 thirds. Okay. And a sub 3 is a sub 2 divided by 3. So that's negative 10 thirds over 3. So that's negative 10 ninths. A sub 4 would be a sub 3 divided by 3, and so on. And so what we're seeing here is, if you wanted to say this sort of in layman's terms without saying too many mathy sounding words, every term is a third of the term that came before it. So every subsequent term is 3 times smaller than the term you just had. So that's called a recursively defined sequence. On the subject of recursively defined sequences, here's another one. So this one is pretty famous. It shows up in all sorts of places, whether that's nature or kind of loopy half sci-fi stories, and that's the Fibonacci sequence. And the Fibonacci sequence is going to give us the definition of its terms in terms of 2 terms that came before it. Okay, so a sub n is equal to a sub n minus 1 plus a sub n minus 2. Okay, and so for this, we need to have the first 2 terms. So a sub 1 is 1, and a sub 2 is also 1. There is no requirement in a sequence kind of like in a function, there is no requirement of this. There's no requirement that all of the terms be distinct. In fact, all of the terms could be exactly the same. So don't allow that to sort of spook you. So if a sub 1 is 2 and a sub 2 is, if a sub 1 is 1 and a sub 2 is also 1, what's a sub 3? So each subsequent term is the sum of the two terms that came before it. So that would be for a sub 3, the sum of the second and the first term. So that's 1 plus 1, which is 2. A sub 4 is the sum of the second and the third term. So that's 2 plus 1, which is 3. A sub 5 is the sum of the third and the fourth term. So that's 2 plus 3, which is 5. And just to kind of get the gist, a sub 6 is the sum of the fifth and the fourth term. So that's 5 plus 3, which is 8. So this is the Fibonacci sequence, and it's a sequence that shows up a tremendous amount in nature. In fact, if we start to look at it, we start to see a lot of really beautiful things, like the golden ratio is rooted in the Fibonacci sequence. It's a really beautiful sequence, and it's one that there's a lot of cool things to learn about. And I'll actually send you guys some videos that talk about the Fibonacci sequence in more detail. We don't cover a ton of it, but I think it's really neat to look at, so I'll give you some more information on that. I want to talk very briefly about two more kinds of sequences that we might not spend a ton of time talking about, but I want you to be exposed to. Specifically, the idea of a geometric sequence . And also an arithmetic sequence. So we'll talk about a geometric sequence first. This is also a recursively defined sequence. So in every geometric sequence, we have a multiplier. That multiplier is sometimes called R, but you'll see it called other things as well. And every term is R times the term that came before it. So in fact, without telling anybody, if we just go back to the previous page, our third example, in fact, sort of our first example of a recursively defined sequence, we didn't say this, but this was a geometric sequence because every term was the term before it multiplied by 1/3. So let's kind of look at another example. So you might have something like a sub n is 2 times a sub n minus 1. And just like with the example that we did here, we have to be given the first term. And with recursively defined sequences, this is usually the case. So a sub n is 2 times a sub n minus 1, and let's say that the first term is 1. Okay? So then we have a sub 2 is 2 times a sub 1, which is 2. A sub 3 is 2 times 2, which is 4. A sub 4 is 8. And so on. And so what you see here in this case is that because the first term was 1 and R, the multiplier, is 2, the terms of the sequence are just powers of 2. You don't want to assume that every geometric sequence is going to be purely exponential like this, because the first term may not be 1. But every geometric sequence has this exponential component that the nth term is going to have a power of the multiplier in it. So I want you to notice here that a sub 2 is 1 times 2 to the first power. A sub 3 is 1 times 2 squared. A sub 4 is 1 times 2 cubed. So if we wanted, we could actually say that a sub n is equal to a sub 1, right? That's our first term, 1, times r to the power n minus 1. So this is an important moment, right? When we have the fourth term, we're multiplying by 2 to the third power. When we have the third term, we're multiplying by 2 squared, and so on. So that is a geometric sequence. You'll notice that perhaps if you compare to the example that we did when we first discussed recursively defined sequences, if the multiplier is less than 1, the terms get smaller and smaller and smaller. So the nth term, if you let n grow beyond all bound, the nth term is tending towards 0 as n goes to infinity. Whereas in this example, where r is greater than 1, in particular r is 2, the terms just keep getting bigger and bigger. And so we see that the nth term is tending to infinity. Really quickly, let's talk about arithmetic sequences. Another sequence that can be defined or thought of as being defined recursively. So here, we, rather than multiplying by something each time, we add something to the term that came before. So a sub n is a sub n minus 1 plus some constant. And we'll just call it k here. You can really call it anything that you want. So similarly, we also need to be given the first term. This is generally the case with recursively defined sequences. You need to know your first term. So let's look at an example. So let's say that a sub n is a sub n minus 1 plus 3, and then a sub 1 is 5. Okay, so then a sub 2 would be 3 plus a sub 1, which is 8. A sub 3 would be 11. A sub 4 would be 14, and so on. So I want you to notice something, just like we talked about with the geometric sequence. 8 is 5 plus 3. 11 is 5 plus 2 times 3. 14 is 5 plus 3 times 3. So since each time you're adding on another 3, what we're seeing is that in fact, a sub n is the first term plus, and notice the same thing, right? When we look at the fourth term, we're adding on 3 times 3. When we're looking at the third term, we're adding on 2 times 3. And the second term, you're just adding on 1, 3. So you could say here plus k times n minus 1. So this is also a recursive definition, right? Each term depends on the term before it, but it's another way of writing it. So this gives us a little bit of a sense of what sequences are, and we'll end this video here. In the next video, we'll just do a couple quick examples where we're not given the nth term. We're actually given the first few terms of the sequence, and we're asked to find the nth term from that. All right. that's the end of this lesson.